Okay, our next speaker is Paula Belzig, and she's going to talk about fault-tolerant entanglement-assisted communication. And the stage is yours.
Thank you. Thanks for the great conference. I'm going to present some joint work with my PhD supervisor, Matthias Cassandra, and Alexander de la Hermes, who's now in Oslo, and I'm from Copenhagen. And yeah, I'm going to talk about fault-tolerant entanglement-assisted communication, which is kind of a consideration of practicality of entanglement-assisted communication to confidentiality. So I don't think I need to motivate very much where this is coming from to this audience, but just as a overview, when I say communication, what I mean is that we're modeling a sender and a receiver, and they are connected by some channel that could be noisy or not noisy. So this could be someone being far away from trying to send like a password to your bank or something, like one person being at a very distant place from the other person. But you could also think about this maybe on the same quantum chip where some parts of the chip are separated than others, or separated by more noisy parts, let's say. So the usual communication setup would be to consider this connection between you and some other person as some sort of wire that is modeled by some probability that the symbol gets corrupted along the way. And your message is some sort of m-bit string, and you want to see how much you have to use the wire to transmit this m-bit string. So you're looking for some best, so depending on you will be given some sort of model, it's assumed that you know a little bit about how your wire will corrupt the information, and then your hope is that you can find the best possible encoder to map your bit string to a bit string that's pretty robust against this noise, and then send it through the channel in this robust form, and then decode it back to a message. And the hope is that this message matches the input. So the receiver should receive a message that is identical with the sender's input message. And in classical communication, what you can do very easily is just send your message many times and do kind of a majority vote. So if there's some probability that your message gets corrupted along the way, and in the end you just check if you have more zeros or ones, then you can decode pretty well. And your success probability of having a matching message will go to 1 if you send n to infinity. But at the same time, you are decreasing the rate a lot, because you are trying to send basically forever until you can say this was successful. And there's a trade-off between having a success probability that approaches 1 and some sort of non-zero rate of channel bits per wire use. And the question is if you can find that. And if you can find some map that puts your information going to the channel and the decoder, then you can ask what is the maximum rate at which I can transmit this, and this is called the capacity of the channel. So that's classical, right? And then in quantum channel theory, people have considered quantum versions of this. Maybe the wire that you're connected with has some quantum properties on its own, or maybe you want to use some quantum effects during your communication. So then there's different generalizations, different assumptions of the subparts of this setup that people have considered, and one of them is set up where the encoder and the decoder have quantum entanglement. So maybe from superdense coding, we all know that quantum entanglement can be used to transmit information. And as it turns out, this tends to be somehow a quantum analog to the classical problem, because in the classical problem, instead of considering this optimization problem over these maps, you can actually calculate the channel's capacity based only on the probability distribution of the mutual information between the input and output of the channel. And there's an analog quantum mutual information which gives you the entanglement-assisted capacity of the quantum channel. So we're still considering classical messages going in. Now this encoder is a map from classical to a quantum state. We're encoding it into a quantum state that's hopefully robust against some channel noise, and then decoding it at the other side and hoping that the success probability approaches 1, but maybe you hope to have a non-zero rate transmitted. So that's all been figured out. and not for a long while, but now in my work, we're thinking about a further quantum assumption that you can make about the setup, which is that if you wanted to actually communicate now between two chips of a quantum computer or between parts of your chip, you would have to find this best possible encoding map and decoding map. It's not really easy to find often, and then we would have to build it out of quantum gates in the gate-first model. So actually, you want to decompose it, I mean, by sort of a GitHub theorem into some sequence of elementary operations, and these elementary operations, they are not noise-free. In the classical setup, this is an assumption that seems quite justified, that your gates are fast enough and noiseless enough to not be corrupted over the duration of this encoding and decoding map. But in quantum, this is not quite clear because it seems that there's some more noise, as we all kind of know, I guess, in quantum computers that is harder to avoid. Because it's also just somehow a big effect of the time it takes to do this encoding, and there's a lot of gates in here for complicated channels. So then what we define is this fault-tolerant entanglement-assisted version of the capacity, where we also want to have fault tolerance assumptions on the gates that make up this encoding and decoding map. So if you're moving into the tolerance into the techniques there, then usually you have to make some assumptions about the noise and about the codes that you're using. So we are, or the gates that you're using. So we are going to assume that the encoding map and decoding map are being implemented, as I said, by sequence of gates by sort of a GitHub theorem. And we're assuming that each gate is subject to Pauli error with probability P. So this is one of the simplest noise models that people consider for quantum computers. It's not clear, or well, it's justified to some degree, I think, by some experiments and comparison between simulation experiment by Google, for example. And there's also a technique to, if you have a more complicated noise model on your device, this randomized compiling to kind of get rid of correlated errors and get back to a scenario where you have approximately this noise model. So we're using this one also because it's quite simple, and this is more of a proof of principle of how well you can even still communicate. But it's also not completely unjustified to use this error model. And then, I mean, as we also all know, if you have a quantum computer and it's noisy, there already exists a bunch of techniques from fault tolerance for encoding some circuit and protecting it along the way. So, I mean, your implementation of your encoding and decoding map, you have some control over this, right? It would not make sense to perform a gate and then we perform the same gate, that would cancel each other. So your control over the implementation can somehow also help to control the noise that these maps have. And in fault tolerance, you have these stabilizer codes where you choose a protected subspace in which you can code the information. And then you can design fault tolerant versions of the gates to simulate basically the same computation, but in a protected manner. And here we're going to be using the concatenated 7-qubit scheme code for this protected encoding. And this concatenated 7-qubit scheme code fulfills a threshold theorem, which is that if each gate here has a probability P of having an error, and this gate error probability is below the threshold, then we can simulate whatever we're doing here with the 7 to the L qubit version. So we're encoding 1 qubit into 7, and then each of the 7 into 7 again, and 49. And we get some logical error that scales like this with L. And that's important because you can basically choose your level so that if you want to have your computation be correct or very high probability, you choose your level L accordingly. There's some trade-off between how many extra levels of protection you have to do and how this scales. So that's good. That means a quantum code can, an error corrected code can protect a computation pretty well, depending on what kind of protocol you choose here, but there's not an immediate result for the capacity of this situation, because in principle now we're using 7 to the L qubits instead of a single qubit in the code, and if you do the naive mode strategy of just considering your whole like encoder and transmission and decoder as one big code and encoding it fault-tolerantly, you're now sending 7 to the L qubits instead of 1, so the rate goes to a way smaller number. You divide by 7 to the L, and this goes pretty high if L is pretty high. So that's one thing that's hurtful about this most naive strategy. And then also in this kind of scenario, you would have your prior model lower the threshold as well, because otherwise the whole thing is not fault-tolerant anymore. So that somehow doesn't give you a good rate to begin like immediately, and or it gives you a rate that will be divided by 7 to the L, and if you set your gate error probability to 0, it's not clear that you recover the noiseless case. So what we showed is that you can indeed instead use some different strategy for based on fault tolerance, but not exactly fault tolerant, based on fault tolerance, so that you can get achievable rates bounded for this fault-tolerant entanglement-assisted information transfer in terms of the usual faultless version and reduced by some little bit, some function here, which scales like order p log p in the gate error. So what that means is that if you set p to 0, you also recover the noiseless case as a rate here. Obviously, this capacity is upper bounded by the usual noiseless one, so then you're approaching it. And you can get some explicit achievable rates as well. Basically, I mean, we know the Fault-tolerant function is pretty complicated, but we can calculate it. So there's some connection that really means that even if you have fault assumptions, you can communicate at this rate, and it's almost the same rate for small gate errors. So that is our result. And now the question, of course, is what is the strategy that can be used there? And the strategy somehow relies on some additional circuit elements. So what we are doing in our strategy here is we want to design some explicit decoding from the code space in which this computation is protected to the physical channel. This part here will also be made up out of gates. It will be the proper decoding from the 7 to the L qubit steam code. 7 to the L qubits in the 7 qubit steam code. And because you're reducing the levels at every step, you're not necessarily in the code space anymore. So it's not exactly covered by the threshold theorem, because you're moving out of the code space at each level, but it's based on the actual decoding from the 7 to the steam code. And then, of course, now moving from the 7 to the L qubits back to a single one to send to the channel, so that the rate doesn't have to be reduced multiplicatively anymore. And so what hinges on our strategy is to show how we can construct these gadgets and these gate circuits that encode and decode from the code space, and show that they fail with a probability that's not horrible. So that's exactly what we do for the 7 qubit steam code, or what actually Alex and Matthias have done also before in some scenario without entanglement assistance, so the proof of this kind of relies on looking at how the error spreads through these gadgets here that decode, and it turns out that we can, with a little bit of massaging, simulate this or understand this as a non-faulty version of the encoding map, together with some effective channel that is applied here. So the way that these decoding operations work, that they are moving at each step from 7 qubits back to 1, so there's some control over how the error spreads. But you cannot entirely avoid any error, so it's unreasonable perhaps to hope for a vanishing error probability of this whole thing, because there's always one final gate before you're going into the channel the last time where you have to apply something to your qubit here, this will always have the probability P of failing in our error model. So there's something proportional to P is kind of also the best we can hope for, and that's what we get with the constant here. So we get that with probability 1 minus constant times P. Everything is kind of fine and behaves as normal. And if with a probability proportional to P, you get something that is extremely noisy and really corrupt. And because there's, so in the usual sense of fault tolerance, you're usually looking at circuits that take classical information as input and also classical information as output at the very end. But here, since there's since we're looking at n copies of the channel, the encoder map acts on everything at once. So it has like that map from n qubit, m bit string of length m into n dimension or n tensor product of the channel. And during this encoding part, it can interact everywhere because there will be CMOS transformed between these encoded versions of the qubits. So the whole thing can be highly correlated. And we're modeling this. So what gets into the decoding interface here can be highly correlated. And we're modeling this by some correlated input. So we are showing, or we show that there is some similarity, equivalence, with some small parameter error here, that you can see this as a channel that takes a highly correlated state as input and normal faultless version of the state you're encoding. Right. So the question also, so there's several difficulties that now arise. So one of them is that there's an equivalent thing for the other triangle, right? Encoding triangle. And one of the things that this scenario brings with it is that your entanglement also has to be put into the code space to be used by your encoding decoding map, and this will actually create mixed states, noisy states, because it will only happen correctly with probability that's proportional to P. So that is one of the difficulties, but it's fixable by entanglement distillation. So what we're using is we're splitting off a really tiny fraction of these channels T here for classical communication and distill it back to perfect entanglement in the code space so that we can use normal noiseless protocols. Yes, so that's one of the difficulties. And the other difficulty is maybe that your model that I just introduced has this correlated state that models how the whole circuit interact with each other. And this leads to an effective channel at this point here that takes a lot of correlated input. So actually, in our proof, we are also at some point, we are as one subpart introducing a communication scenario that is based on normal channel coding, but has to do with this input state. So if you have some channel that acts on the loop space A and maps to B, you can consider a bigger channel that takes also the syndrome space as input, the space that has the correlated state in it, and you can construct this channel that with some probability traces out the extra space, and with some probability it does something horrible, but we don't know anything about it and we don't assume anything about it. And then you are looking at a communication scenario where you take n tensor product from this channel with some input state that is correlated between the inputs. So there has been similar considerations actually by a group in Munich in Holger Bocker's group, where they call this sort of communication scenario in a similar way. They call it jamming the jammer. It's jamming the channel. But in their case, we also put some coding theories for that, but they have an assumption on the dimension of this state. So they consider a jammer putting in some state into your channel that is tensored with your normal input, and your output has to kind of take that into consideration. They can do something there, but for us, first of all, this is where non-IID things come from here, but also for us, this state that models all of the happenings in the encoding circuit has a dimension that grows with the number of channel copies. So you cannot have the same assumption, so you need some other thought has to go into that. So it's not exactly the same scenario. If you could assume some stuff about this state, then you could probably maybe, if you can assume something about the dimension of the state, then you can map it back to the scenario that was considered by a Roberts group. But in general, if you have no assumptions, then you cannot deal with anything with the state. And because we're wanting to make a statement about any channel, so any encoding circuit, any maybe even later any full model, that's about the vision, and then we don't make any assumptions here. And then this hurts us, but it's sort of a worst case assumption, like a worst case correlation we can have in the state. So then what we do in our paper is we prove a coding speed for this kind of model, which we refer to as arbitrarily varying perturbations to the channel, and we introduce a post-selection-like technique to map this back to a scenario where you can use the techniques from IID scenarios. Okay, and yes, so that's the other big difficulty, but together these difficulties can be overcome through the entanglement distillation and this post-selection scenario to actually arrive at an achievable rate where it's only reduced by some function of p, and this function has to do with the entanglement distillation. So I'm just listing out what we're paying. I didn't want to go into the detail more, but then we're paying a little bit for distilling entanglement to reduce this array because we're taking away some cheese, and we're paying something for this coding, a coding error that doesn't necessarily go to 0 with this Q in a way that we would hope. And we pay something for continuity because we're actually having an effective channel here that is like the original channel with some probability P, or proportional to P. And so we're also actually designing the best encoder for that channel. So we pay something for a continuity relation between the two. Yes, that already brings me to the end. So I hope I sort of convinced you that you can still communicate at almost the same rate with some noise assumptions if you are clever about designing your encoding and decoding. And we also recover that the usual case is the case that's noiseless, straightforwardly from our considerations. And then, of course, the open questions, we are assuming a specific noise model and we're assuming a specific code. We're using somewhat heavily this concatenation structure in the proof. There's some questions about how this could be generalized. And there's also our channels have the assumption of the dimensions. We also extend this maybe to infinite dimensional channels. Maybe some very low level experiments, at least some people have once thought about this. But yeah, that's it. Thank you.